In today's video, we're going to take a look at Anthropic's most recent announcement. They asked an unreleased version of Claude to take a stab at the Riemann Hypothesis, and they found that it increased the lower bound for the fraction of zeros on the Riemann zeta function that satisfied the hypothesis from 41.6% to 67.2%. So this video is going to be explaining what that really means. We're not going to go into too much detail, but yeah, let's get into it. Let's start off in 1792. So we had Gauss, and he was studying prime numbers. He wanted to try and find a pattern or a function that allowed you to find how many prime numbers existed up until a certain point. So he called this function pi x, where as you input a number, it tells you how many prime numbers exist up until this point. So you can see here on this real axis, this number line, as we move up, the number of prime numbers that exist up until then increases, and we can plot this in 2 dimensions like this. So there we are, we have this staircase, and it shows it goes up at every prime number. So if you go to a point in the staircase, say 10 along the x-axis, you'd find the corresponding y value that tells you how many points, in this case 4, of prime numbers exist up until that number. So that is this graph. And now let's look at it a different way. If we look at the prime density, this tells you basically where each prime lives. So we have 1 at 2, 1 at 3, 1 at 5, 1 at 7. So let's look at that on a different scale. Instead of looking at the prime density for every number, let's look at the prime density in groups of 10. So the first 10, 0 to 10, there are 4 prime numbers. Between 10 to 20, there's 4 prime numbers. Between 20 to 30, there's 2 prime numbers, and so on. There's not really a pattern that's emerging here, so let's increase the group size and see if there is. So in 100 primes, you can see the first 100 has 25 primes, the second 100 has 21, the third 100 is 16. And then we'll look at it with 1,000, and we're starting to see a bit more of a pattern emerge. So within the first 1,000, there's 168 primes. Within the second 1,000, there is 135 primes. And what this really means is that if you took a random number in the first 1,000 numbers, there is a 168 out of 1,000 chance that that number is going to be prime. So what we can do is we can create a function on top of this. This function looks like this. It's the inverse of a logarithm multiplied by the batch size. So we're doing batches of 1,000, so we get 1,000 over log x for this function. And what this function tells us is basically the likelihood of a number being prime at any point. So we can increase this as well. This is what it looks like over 10,000. We see that the data starts to fit this curve a bit better, and the function changes to 10,000 over log x. And here the same thing happens at 100,000 over log x. And here at 1,000,000 over log x, it keeps on increasing. The data gets closer and closer to this function. So let's look at this a little bit of a different way. Let's integrate this curve and so find the area underneath it. And you can see as we plot here, as we go across, we're plotting the area underneath it, which basically represents the total number of primes up until this point. As this was the prime density, this is just adding up all the primes, but using the function now that we've created. And what this gives us is a function called lie x. So lie x is the formula that we just derived using the inverse logarithm, and it's basically a nice way to visualize an approximation of pi x, which was the step graph that Euler was talking about at the start of this. Gauss was talking about at the start of this. So there we have it. We have lie x, which is the blue curve, and pi x, which is the stepping up curve, or the stepping up function. So what we see is there is a big error between these. It doesn't exactly match it. So let's take a closer look at this error. We can normalize this lie x function, and then it changes the shape of this error, and this is the error we see. So there's no pattern to this data, as you can see, and the real thing that Gauss found here is that if we could find a way to create a formula for this error, then we could just subtract it from lie x, and we would get the pi x formula. So yeah, it basically created a goal. We need to find a way to formalize this error, and if we can do that, then we'll be able to formalize a formula for prime numbers, basically, to explain how many prime numbers you'll get at each point and where the prime numbers lie. It's quite a tricky question now. So Gauss didn't manage to get there himself, but he left it in a state where we have this error plot. And so now let's pick it a different thread this is in 1737 we had Euler, who was looking at this zeta function, which is just 1 over 1 to the power of s plus 1 over 2 to the power of s, etc, etc. If you plug in a value of s, let's say if you plug in 1, you end up getting infinity. As you can see, this goes up forever, but as you increase the power of s, it ends up stabilizing on a point, so you get these values here. So let's plot this. You get this sort of curve that you see here, where it diverges to infinity as you get towards 1, but after that it stabilizes at a certain point. So let's pick the value of 2. So the value of 2 is an interesting one. This is a value that Euler calculated to be pi squared over 6, which deserves its own video explaining how that works, but we'll just take it for granted for now. But yeah, if you take this function where s equals 2, you end up with this 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. And if we expand those out, we get 1 over 4 plus 1 over 9 plus 1 over 16, etc. So Euler found you can do something quite interesting with this. You can organise each of these terms into different groups. So you can see how these are organised here. What we've basically done is we have on the left side we've got different families. So we have 2 family, 3 family, 5 family, 7 family. There's a family for each prime number. So it would go on to there'd be an 11 family as well and a 13 family. And what the idea is that each term factorizes into one of these groups. So and we're focusing on the denominator of each term. So the 4 here goes into the 2 family, the 16, the 64 go into the 2 family, the 9, the 81 go into the 3 family, the 25 goes into the 5 family, and the 49 goes into the 7 family. And then we do have terms like 36, which don't really have a home anywhere. They would go into the 6 family, but 6 isn't a prime number. But what we find is that each of these terms that doesn't go into one of these families can be created by combining 2 different terms from the other families. So it's not exactly primary. It's not a prime factor the same way that the other ones are. So we don't really need to account for that. And now let's take a deeper look inside these families in particular. So Euler showed that you can do a little bit of algebra, do some rearranging here. So you multiply both sides by 1 over 4, you rearrange the equation and you take out a factor of s2, and then you can rearrange to show that s2 is 4 over 3. So the prime factor families for the value of prime 2 is 4 over 3, and you can do the same thing for 3, which is 9 over 8, 5 is 25 over 24, and 7 is 49 over 48. So I'm sure you can see the pattern emerging here. But let's take a look now at the original term. So this was the original term up here, and one thing you notice is let's circle each term, okay? Each term on the top equation can be created by a combination of the terms from each of these families. So the 1's just a combination of all the 1's, and then as you go through 1 over 4, it just changes which selection you've got on the 2 family. Something interesting happens when we get to 1 over 36 though. So like we showed before, this selects 2 of these values we get the 1 over 4 from the 2 family, the 1 over 9 from the 3 family, and then the rest will be 1. And the same thing happens at 100, so we get 1 over 4 and 1 over 25 and the rest are 1. But the point is that every single term in this top equation can be created by a combination of the terms from these prime families. Obviously these primes go on for the rest of the prime numbers, but yeah, the idea is that each combination will create one of them. So by that logic, what it ends up meaning is that you can multiply all these prime families together and it will equal the top equation, because it will expand all of them out to create every possible combination of each of the terms, which are then all encapsulated in this top function. So it creates this interesting idea where the zeta function can be written out in 2 different ways. One is the sum of all these different functions up here, and one at the bottom for all these as the product of all these prime factor equations. So let's take a look. You can see here what that equals. And this becomes a generic formula. So for different values of s, this doesn't just work for 2. As you change the different values of s, this still holds. The only value of s it doesn't hold for is 1, because at that point it diverges to infinity. So that was what Euler found. He found that this identity, which basically says the zeta function can be represented as a product of the prime factors. So we have Euler's contribution here with the product of the prime factors. We have Gauss's contribution with the error of the primes, and then we have Riemann coming in. So he looks at these two outputs and he adds his own little piece to the pot before mixing it all together. So he takes a look at the zeta function that Euler was looking at, and he plots the input and the output on a real number graph. So you can see here, as the yellow number changes, which is the input, the blue point changes as well, which is the output. And we don't really go below 1, because then it would diverge to infinity. And he finds an interesting way to represent this. So as we change the yellow line, the yellow dot, which is the input, we can represent the blue dot as a sum of converging arrows. So each arrow is smaller than the previous one. And what these arrows represent as well, the first arrow represents 1, the second arrow represents 1 over 2 to the power of s, the third arrow represents 1 over 3 to the power of s, and this carries on. So each arrow represents the following term, and they get smaller and smaller and smaller until they converge on a point. So this is just a nice way to visualize it, and it makes it easier to understand what's coming next, which is what Riemann does is he expands this out into the complex plane. So he adds an imaginary axis. And if you know much about the imaginary axis, what it really does is it adds phase to things. So to not overcomplicate it, let's just kind of show you what happens. As you increase the imaginary component of the complex number that is the input, the output basically adds phase to each of these arrows that are stacked up and rotates them around, creating this type of curling effect. And this is how adding imaginary components to the input affects the output. So it's a bit of an interesting concept, this. But this is all complex analysis, so this is what Riemann was good at. So an interesting thing about this is now we can create this plot. Okay, so let's take a look at what the axis looks like on the right side, and then let's apply the zeta function as a transformation to that. And it changes its shape like this. And so what Riemann did was say, what happens if on the left side of this equation where there's nothing allowed to be done because it brings off to infinity, let's do something called analytic continuation. And what that is it just expands the same shapes that existed on this side of the graph and puts them out to the other side of the graph where they would naturally continue if they were allowed to continue past the infinity point. So it creates this graph that has been analytically continued. So Riemann found that if he looks at this graph now, there's certain input points that would lead to an output point of 0. So now we're allowed to look at the left half of the graph, to the left of the point 1, which before it went off to infinity, so we never looked at. And now if we put an input at this point, half plus 14.1347i, we end up with a 0 output, which is strange. And it's something that Riemann wanted to investigate further. So he started plotting out, he started trying to find the points where this hit 0. And what he found was that every point lay on this half line here, this yellow dotted line representing half. So as we go up the complex plane, as we go up the imaginary axis on this real number of half, we can see how that changes the output. It starts to turn around like this, all the phase changes, and it comes back and hits 0. And Riemann was checking all this by hand. He worked out the first few values, the first few zeros by hand, which was not an easy thing to do. And he ended up coming up with this formula. He basically said there are infinite many zeros, so there's infinitely many points on this half line that has an output of 0. and his idea is that they're all trapped in this strip. Every single zero will be on this half line. And the reason he came to this idea was this idea of symmetry. So we're not going to go too deep into that in this video, but I'll cover the basics. What he found was that if you took any point to the left of this half line, there would be a corresponding point that is symmetrical to it about the half line that would have the same output. And so this symmetry was along this half line here, and that's why when you converging it down to exactly on the half line, that's the only place where the zeros can exist. And that is what Riemann's hypothesis is that all the zeros lie on this half line. So the way that he was checking these zeros is using this function here. This was like, he was keeping this a secret, it was in his notes. And that doesn't reveal where the zeros are, it just gives you a way to check if an input is a zero. So that's how he was figuring out where the zeros are. So we then have these three ideas. We have the first idea, which is Gauss talking about the errors in relation to this lie versus pi function. And he was trying to find a way to formalize what these errors were. And then we have Euler with his zeta function and his product of primes function. And then we have Riemann with this finding that the zeros lie in this imaginary component of the half number in the complex plane. So how do these combine? So let's look back at Euler. If we take a logarithm of this function on both sides, what we end up getting is this. It ends up being a sum of each of the terms. So instead of being a product of each of the prime families, we get a sum of each of the prime families equals a logarithm of the output. So Riemann took this and applied this to his work. So the way that he did that, first of all, is let's take this complex graph and let's expand it into the z dimension. And so what we're doing here, since this plane here, this two-dimensional plane, is the input plane, what we're doing here is we're kind of representing the output plane on the z-axis. So this is the output. You see the 0 points stay at 0, and then the other points land at the place where they end up converging. There are some points that go off to infinity, but this is the sort of shape that emerges. And so then if we take a logarithm of this output shape, it changes it, and all the zeros go off to negative infinity. So let's show you how that works. Like this. So this is the logarithm of it. And what we end up with is, the zeros go off to negative infinity. There is a pole here, and a pole is where it goes off to infinity, and that is at s equals 1, which we showed at the start why that one goes off to infinity. So let's take a look at the right half of the right part of this shape, where s equals 1. So for example, at s equals 2. If we take a look at s equals 2, the height of it in the z-axis can be represented as a sum of the different prime families. So here you can see that the log of the output of the zeta function at s equals 2 is the same as the log of the output of the prime families at s equals 2. So we have the prime family here in blue for the 2 factors, the 3 factors, the 5 factors, it goes on. So this is an interesting way to relate Euler's formulation of the product of the primes to Riemann's complex plane version of the zeta function. You can see here that every value works like this too. So Riemann used this to create this machine, and we'll talk more about this machine in a second, but what he basically was able to do is extract features from this graph and use them to compute something about primes. So the features that he extracted were the poles and the zeros. So the poles are where it goes off to infinity, so there's only one pole, and that's when s equals 1. And then the zeros are where it goes off to negative infinity. So that is all the points along this half line that have an output of 0, they are the zeros. So let's take these out of the graph and represent them in a more discrete form. So the pole we represent we represent something being a pole by giving it a negative initial value, so that's the -1, whereas the ones below it all have +1 initial values to show that they're zeros. And then we have that on the left side of the coordinates, and on the other side is just the complex coordinates of where that point exists. So the pole exists at s equals 1, there is no imaginary part of it, and then the rest of the zeros exist with the real part of the half and with some imaginary part on top of it. So we've extracted these features from the graph, and now Riemann managed to use the prime product formula, the logarithm stuff that we were showing you before, to do some interesting transformation of these points. I'm not going to go too deep into how he did this transformation now. You've got the ingredients here, but I want to keep this video relatively short, so I might go into more depth in this in a future video. But he basically created this machine that converted these poles and zeros into functions. And so the pole was converted into the Lie-x function from the start of the video. And this is the function that predicted the pi-x, but was a little bit off. So remember, if we zoom in, you might understand it a bit better. Remember, we had the pi-x, which showed the staircase of where the primes were, and the Lie-x was the approximation of that. So what Riemann did was he managed to create a machine that converted the pole into the Lie-x function, and then that same machine would convert the zeros into waves along this sort of function line. So you can see all these zeros transform into different waves. And the interesting thing he found is that if you add up all of these waves, they account for the errors between the Lie and the pi function. So if you add up more and more and more waves, it ends up approaching it exactly. So that's interesting there. So what he's saying there is, if we found all the zeros and plugged them into this function, we would be able to plot the pi-x function. So let's take a look at what the error actually is. So here's the cumulative error, and this is what we need to solve, this is what we need to find the pattern for. This is at a bigger scale. So if we take all the zeros that we extracted from the graph, and we can see them represented as waves now, and as they're all added together, eventually they converge exactly on this error function. So that's brilliant, we've figured it out. Now we have a way to combine all this and find the product for the primes, right? Because we've used Euler's prime product formula, took the logarithm of that to find the relationship between the zeta function and the primes, and then we've used Riemann's complex presentation of the zeta function and related it to Euler's identity to then extract features from that graph and convert these into information about the prime numbers that Gauss was talking about before. And so now if we find all the zeros, we can plug them in and we would get this error graph perfectly. And once we've got this error graph perfectly, we can subtract it from the Lie function and get the pi function. And so we would find the formula for all the prime numbers. So, brilliant, right? The only problem is we don't actually know all the zeros. The way that Riemann was finding them before was using the formula to check. And we've got a formula to check if a point reaches 0, but we don't have a formula to find all the zeros, and that's very hard to do. So people have been trying to do that for a while, and it's not so easy. But there's other things people have done, okay? So whilst we've been trying to figure out what the formula is to find all the zeros, other people have been doing work based on the assumption that the Riemann hypothesis is true, which is that all of these zeros lie in this point of the half on the half plane. So if that's true, that all the zeros lie in this half point, then all these different conjectures will also become true. So a lot of conjectures have been created that are relying on this, that have been built on this Riemann hypothesis. And we need to prove that this is true, the Riemann hypothesis, to then prove that the rest of these are true. So there's a lot more progress that has been made that is building on top of this, and that's why people are trying to find proof that the Riemann hypothesis is true. So how have we gotten along with that? If you take a look at this half function, you convert it around, you can end up creating this wave here that crosses the axis every time there is a zero. And this allows you to do some interesting work with it. It involves some interesting maths. We're not going to get into that here because we're trying to keep this brief. I might cover this in the next video as well. But here is the progress that has been made on trying to prove that all of the points lie on this line. So in 1914, a man called Hardy came along and proved that there is infinitely many of the zeros that exist on the line, but that as a percentage it could be 0% of the total, so that doesn't really prove much. That was the starting point though, and he used some interesting methodology for that. Yeah, we'll go into that in the next video. And then in 1942, a man called Selberg came along and he proved that a positive proportion of the zeros must lie on this line. And the way that he kind of did this, I'll give you a brief rundown, is first of all he figured out how many zeros must exist within a certain number n, and then he found a way to figure that out, and then he figured out how many zeros can he prove exist up to a certain point n, and what he found was that there was a positive proportion. Levinson expanded on this in 1974 and proved that up to a point n, at least 1/3 of the zeros must lie on this line. And then in 1989, Conroy came about and did 2/5. In 2020, it was proved to be 41.6%. And then in 2026, the most recent announcement, Anthropic announced that Claude has found 67.2% of the zeros must lie on this line. So there is some interesting maths that goes into this, but it's quite complicated, so we'll save this for a future video around how Claude actually figured this out. But this is more explaining what was figured out and why it is important. So yeah, thanks for watching this video, and I'll catch you in the next one.